Um, any questions before I get started? All right. All right. Today's lesson is useful. It's going to help you with your project. I've been working on your project as well, and I think it's step 7, somewhere around there, where you need to find um, the fetal weight function. Like,
Yeah, the antiderivative, right?
yeah, the antiderivative, and then also take into consideration the initial conditions they give you. Today we'll explain how you can use the things that we're doing already now to figure that out. So, oh, that's going to be the focus. So let's see. The first thing I want to do is a problem with you to show you a new relationship between the integral and distances. Let's see here. All right, I'm going to share the screen. So this is section 4.4, fundamental theorem of calculus. So we're not doing Riemann sums. Last 2 classes, we were talking about determining the distance traveled from velocity and the definite integral, that notation that we were doing. Okay. Fundamental theorem of calculus, you're going to see that we've been already doing that, but today it's going to try, I'm going to try and bring in some more ideas behind the integral. So the first thing is, let's just a quick understanding of what we know the integral to be at this point. If we were to say, take the integral of some function between 2 intervals, a and b, that we're trying to calculate the signed area underneath that curve, between that curve and the x-axis, over that specific x interval, right? And we saw that if the function is below the x-axis, we're going to get a negative area, because that's what it means in terms of the integral. And when it's above the x-axis, it's a positive area, and that we can break up the integral into different pieces to suit our needs. So it might be specifically because it's a piecewise function, or it might be because it makes it easier because it's an absolute value function. Whatever the reasoning is, but we have the ability to break up the domain, use the definition of the function appropriate to the domain that you're in, and just calculate those integrals and add them all up together as one. So today we're going to see one more relationship, and this is more of a physical relationship to the laws of physics and things like that. And it's going to help with the fetus stuff, because it's more about growth and things like that. So let's look at this problem here. It says a student, and think of when we're going through this problem today, I want you to, hopefully you've been working on the project, think about how this problem is relative to maybe the functions you've been working with and the problems that you're being asked, because this is meant to help guide you with this. All right, so a student with a 3rd floor dormitory window 32 feet off the ground tosses a water balloon straight up into the air with an initial velocity of 16 feet per second. So he or she is taking the water balloon, not tossing it out, but tossing it straight up into the air. So their hand is out the window. And the rate that they're throwing it at up is positive 16 feet per second. It turns out that the instantaneous velocity of the water balloon is given by this formula. So the velocity of this balloon is modeled after negative 32t plus 16, where v is measured in feet per second and t is measured in seconds. So first we should look at the velocity function and take what information we can from it. Okay. Let's get rid of this and this. Here's the velocity function. So one thing I've done is I've restricted t to being greater than or equal to 0, because it wouldn't make sense for time to be negative. And what I see here is at time 0, when this water balloon is first thrown into the air, it has a velocity, because this is the velocity graph, of 16 feet per second. That's the force that that person put into that water balloon. I can also see that, as time goes by, I see that the velocity is decreasing. It's positive. It is a positive velocity, but it is decreasing. But it is positive. So it's still going up. Here it's 16, 1 second later, or what is this? Oh, this is a second. So this is 1 second all the way over here. So a tenth of a second later, it's traveling at 12.8 feet per second up. So it's still gaining feet. And that continues. It's still gaining feet, but at a lesser rate, all the way down to 1/2 of a second. So this is just from this velocity formula that we've been given. So from the first moment all the way up to 1/2 of a second, my water balloon is going up into the air higher and higher. So it's gaining distance from the ground. But at 1/2 a second, it stops gaining height. Its velocity is no longer increasing, it's 0. And then after that, its velocity is now negative, which means it's moving. It has a speed, but it's in the opposite direction. It's going down now. So at 1/2 of a second in, we hit the peak height that this water balloon is going to travel up, and then it starts to come down. And notice as time goes by, at 1 second, it is falling at a rate of 16 feet per second. And it's increasing. Every moment that goes by, that rate is increasing more and more. It doesn't tell me notice what this velocity function doesn't tell me. It doesn't tell me when this water balloon hits the ground. It can't account for that. I mean, clearly, when the water balloon hits the ground, it will have a velocity at that time then of 0. Once that moment's happened, once it's hits the ground at a certain velocity, fast, and then it's done. It's on the ground. Now it has a velocity of 0. This function does not account for that, and it can't show us that. And it can't do that. But from this function, we can get that information. And this time, instead of thinking about the area underneath some curve, what we want to do is think about the relationship between the position function of something and its velocity function, because they are related. We've seen that. We've seen that if you take the derivative of the position function, you have the velocity function. That's how we find the instantaneous rate of change on a curve. Take the derivative of that function. And so we have that function. That's what we're starting with. So we're not starting with the original function, we're starting with the derivative. But if we can go backwards, which we can using antiderivatives, we can find the original position function. And the position function will tell us when it hits the ground, because we know what that would be. That would be when it's equal to 0, right? When the height, the position of the water balloon is at 0 feet. So let's take the antiderivative of this. And this is the specific process that is being asked in question number 7 on the project. You're asked to find the original function, and then you're given initial data, which we're going to use in a second here. So let's first find, let me see if I have this typed up in Word. I don't, this is not a Word thing yet. Okay, so let's find this position function. So I'm gonna represent it as S of t. It's the antiderivative of this function. So that negative 32t is going to have to be something t squared. We're going backwards. So it had to have come from a quadratic. So it's going to be a negative 32t squared, but it's not negative 32 because when I take the derivative of this, I get 2 times negative 32 would have given me a negative 64, but I got a negative 32 here. So the easiest way to deal with this is I keep the number that's there, the negative 32, and I divide it by what the exponent is now. So that now when I consider this derivative, the derivative of this, 2 times this 2 cancel out, and I'm left with negative 32, which is right up here. This will always work. All right, and then the 16 is easy because that had to come from a linear because this is a constant. So that's just plus 16. 16, sorry, plus 16t. But that's not the antiderivative. This is one antiderivative of many, and we saw that we can represent all of them by the concept of adding a plus c, some value that c can take on. When I do that for Desmos, it even asks me, do you want to allow it to take on a whole bunch of values? Yes, I do. See? All of these different c values still have the same velocity information at the same exact time. At 1/2 of a second, the velocity is 0, no matter what my c value is. And that should make sense because when you take the derivative of that position function and you go to take the derivative of that constant, it's 0. The derivative of any constant value is going to be 0. So it doesn't affect your velocities. They're all the same. So now ours, though, is very specific. It's got to be to the fact, it's got to match our initial data. And what was our initial data? Our initial data was that this person is throwing the ball from a window that is 32 feet off the ground. So in terms of our position function, I know that at time 0, this water balloon is 32 feet above the ground. And that, I'm going to color that purple because that's part of the position function. So look at my current position function when c is equal to positive 10. That's not correct because this isn't intersecting that. So this has got to go larger and larger. I'm going to set this all the way up to, let's say, 40. So from 0 to 40. Now let's play with that number. We're just going to raise it up until we get to it. Oh, it happens to be exactly when, in this case, when c is equal to 32. Now, that's not how we do this mathematically. Solve it. We set it up in Desmos and then just try and find it out that way. There's an easier way. You know the formula that's going to be used. So you need to solve the problem. You know that when you know that s of 32, sorry, s of 0 is equal to 32. That's the given data. You're given that in this project. You're given something like on day 112, I think it was. The fetus weighs this amount, something like that in grams. And so this is similar. So yours would be, you know, the W of 112 is equal to 100 grams, if that's what the data is. Okay, and here, in this case, it's S of 0 is equal to 32. At time 0, the water balloon was at a height of 32. Because remember, we're looking at the speed, the velocity at which this water balloon is moving. That's the original function we have. But now we're thinking about its position. And so if S of 0 is equal to 32, I can plug 0 in for t. I can solve S of 0. That's negative 32 over 2. And that's just negative 16, right? But 0 squared plus 16 times 0 plus c, what is it equal to? Is equal to 32. We know that. We were told that at time 0, the answer that when you put 0 in the position function, you're going to get 32 out. And so I know when I'm putting 0 in for t, this is what happens. And I'm left with, in this case, c is equal to 32. So on the project, you don't have 0. What does that mean? Well, it just means that your math is going to be a little bit more difficult to do. Use a calculator or use Wolfram Alpha and put it in, or use Desmos and let it do the calculations for you. But you're going to have to put in like 112 where these zeros are. If the data was on day 112, where those zeros are, you would be putting in 112. You'd have a C value. You'd have some other value over here. I think it's 100. And then you'd solve for that C. And then you'd have the real equation for that fetus growth. You'd have the actual fetal weights per day. You'd have a model for that. All right, so let's go back to this. So we know that then C is equal to 32. So this is the original function. That's the position function. I'm gonna clean this up. 32 over 2 is 16. So our position function has, specific to this data that we have this 0.032. Get rid of this stuff here. All right. This is the position function that shares this velocity function with many other functions. All right. So this is its velocity, but because of this data point, we know that this is definitely that. All right. So that's the one thing that we can now think about in terms of using the process of antiderivatives to come up with position functions when you're given initial data. But here's the next thing that we can do. We can measure distance traveled. Go back to one of the most important things that we studied in pre-calculus, and the thing that continues to come along with us in calculus, we try to go to it whenever we can, is distance is equal to r times t. Distance traveled is some rate, some constant rate, right, at some amount of time interval. And the multiplication of those two, the rate and time, the area of some rectangle that it forms, represents total distance traveled. That's when the rate is constant. Well, maybe the rate doesn't need to be constant. Maybe instead of distance is equal to RT, maybe R, instead of representing a constant rate, represents a function that can give you a rate at any moment in time. They just don't have to be constant. They might be. Maybe at every moment in time, the rate is 25 miles per hour. Maybe. But maybe it's not. Maybe the rate at each individual time is something specific. And then we have this process now with integration that allows us to tie it all together. So we can do distance equals RT with not a constant rate, but with anything. And that's what's happening here. This is a function, this is a water balloon that takes on a whole bunch of different rates. Every moment it's traveling, it's taking on a new rate that it's traveling at. In the first half second, it's increasing. The rate's not increasing, but it's going up into the air, right? Its velocity is positive. Its rate is decreasing as it's going up higher and higher, up until it gets to 1/2 of a second where it's no longer increasing at all. The rate is 0. And then it starts to decrease, and the decrease is increasing as time goes by. So we've seen that. So this can measure that. It can measure those rates. So distance can still be measured here. And what we should realize now is, I mean, let's look at this problem right here. This is a perfect example. This is an easy one for us to think about. Think off the top of your head. You threw this water balloon from your dormitory window at 32 feet. You threw it up into the air at a certain rate. It hits some maximum peak. Now it only goes straight up and down. It goes straight up to a certain height, and then it comes straight back down, passes your hand, and goes until it hits the ground 32 feet. Since it's past your hand, it's gone up a certain amount of distance. So I don't know the full path it's traveled yet. How far has it traveled? What's the distance? Now, I'm not saying what's the total distance of the path that is traveled, but what's the difference in the distance from the ground to the window? It's just 32. How do you measure that though? I mean, you might be saying, well, that's obvious. You're 32 feet above the ground. It's just 32 feet. So that's the distance. Yes. But that's specific because we're choosing the ground as our level. We could have chosen anywhere. And if we didn't choose that ground, then what's the distance? It's 32 minus whatever that level is, the distance from the level to the ground. And that will tell you that distance that you've traveled. So what is that in terms of this function then? Well, it's 32 minus 32 is this, s of 0. And this is minus, and this, sorry, so it's not the, yeah, it's actually 0 minus 32, right? What's the total distance traveled? Negative 32. We've fallen. So it's s of 2, the value of this point right here, minus the value of this point right here. That's the total distance traveled from this balloon's point right here, where it starts, to the ground. It travels down 32 feet, right? It's going to go up a certain bit. We're not counting the total path distance. We're just counting the difference between the two distances. And the integral is going to actually give us that, because what is this? This is s of 2 minus s of 0 gives us negative 32. Where have we seen this s of 2 and this s of 0 before, where we subtract something? It's when we were taking the integral. If we take the integral of v of t from some time interval to some other time interval, right? So let's go from time 0 to when it hits the ground at time 2. If we take that time interval, so the integral of v of t from 0 to 2, what do we get? We end up getting negative 16. Right? Remember, we have to plug it in, so we're going to get s of 2, which is 0, minus s of 0, which is negative 32. That tells us the total distance. That is the integral of the velocity function from 0 to 2. Because the integral of v of t is s of t. And remember, we take the bar and we put the 0 to 2, and then we move it to the straight bar, and we put 2 to 0, and then we plug them into the function that we got, that antiderivative. Well, the antiderivative is s of t. And so we just calculate this by doing s of 2 minus s of 0. This may sound a little confusing. I'm going to move us over to Word. I think the Word write-up that I have where I give you the theorem itself will be valuable to clearing this up. All right, here we go. All right, so let's start right from the top. Some of this I'm going to repeat, but it's good to see it written out. So distance is equal to RT. This concept can now be represented by the concept of the integral of some velocity function over some time interval a to b. That's our r. The t part is your dt, delta t, the change in time, the amount of time that has elapsed. That is all built into this. So distance is equal to this. The distance of something is equal to that in terms of just like this RT. One good way of thinking about this, because I think one thing that can be confusing, is the fact that we're not talking about the distance of that path that it takes. And so one way that I would suggest you to think about this is, think about us driving somewhere, and we're going to plot some data. And the data we're going to plot is the amount of time we've been driving in hours, let's say, and the distance from home we currently are. The distance from home. And when we drive, we start driving and we're leaving, we're going away from our home. And so our graph is going up. As time goes by, it's going up because our distance away from our home is increasing. I go to a store, now I stop. Time goes by. It flattens out because I'm not going anywhere and the distance from home is not changing. I get back into my car and I start driving again further from my home. And so as time goes by, the function continues to go up a little bit more. I stop again, flattens out for the amount of time that I'm in the store, and then I get in my car and I start to return home. But I make one more stop, and this is where we stop the problem at. So the graph went down a little bit, and now we stop. And so that's the data that we're going to work with. And the question is, how far am I from home? Or how far am I from my starting position? And that answer is the distance that you're at currently, not taking into account all the other places that you stopped at, versus the distance of the very beginning. So that hopefully that helps a little bit with the understanding of why we don't measure everything. That's not what this problem does. Calculus does provide an answer actually to that. That's in Calc 2, I'd say. I don't think it's in Calc 3. I think it's in Calc 2. So distance equals RT is the same thing as saying the integral of some velocity function over some time interval from A to B, where that time interval is closed. Okay. And so now we can think of R as a function instead of just a constant. And so when you put some time into R, it gives you the very specific velocity at that moment in time. And we can add them all up. And we add all of those values up together through our integration process. That's what that is. It's a summation process. We can get what we're looking for, the total distance traveled at this point. So all of this right here relating this to distance equals RT is actually, this is just the fundamental theorem of calculus. So this is the theorem that we really stop with in Calc 1. If f is, so here it is. So if f is a continuous function on some closed interval AB, and capital F is any antiderivative of that lowercase f, right? Because there's a whole bunch of capital F's that has that f as its derivative, right? All those C's that it can take on. So as long as this is true, f is continuous on the interval we're working on and the interval is closed, and capital F is the antiderivative of that function we're thinking about, then the integral from A to B of lowercase f of x dx is equal to capital F of B minus capital F of A. That's not new to us. The only thing new here is that it has a name, and this is a theorem. This is what we did the last 2 classes, was learn about this notation, what it means process-wise, taking the antiderivatives, and how to come up with a numerical answer. But this is the fundamental theorem of calculus. It's this relationship. So given this fact right here, this relationship is definitely true. And we're seeing more and more meanings. The one thing that we saw, what we were first operating the last 2 classes on, that this was representative of the area, signed area underneath the curve. Yep, and it is. And that's the same exact thing as with the distance equals RT. We saw this when we started all of this. Distance equals RT was the area of a rectangle. And so a positive distance traveled would be a positive area of that rectangle. And it was the area under a constant curve. Constant, so it was just flat, horizontally flat. So this is all just being tied in together. Note here, this is the stuff that we've been doing the last 2 days. This is the official notation, right? This is what this means. F of x with the bar from B to A. This is calculus notation right here, is representative of this concept f of b minus f of a, in that order. It's the top one first minus the bottom one. So, right, so that's the whole, we plug it into our antiderivative and get those numbers and subtract. And so this is what we were using the last 2 classes. The integral from a to b of some function f of x dx is equal to its antiderivative, capital F of x, from b to a. Remember, we didn't have to find a c value. Think about that, and think about why. It's because when you calculate f of b and f of a, the c value is constant in both. It's the same thing. If, let's say, it was like 16, I think in that last one, right? 16 and 16, what are you subtracting them? They're going to always cancel out. So that's why you don't need to find the c value when you're doing this process of what we call definite integrals. Definite. So this is what a definition of a definite integral is. So you get its antiderivative, you write this notation-wise, it's good so that we're making note of what we're doing. And then that's equal to this. And then so we have this written out nice, and then we do these calculations, f of b minus f of a, and that is equal to some signed area. It is equal to some distance from where you currently are, from where you started. Right? It doesn't, s of 0 does not have to be 0. Your home does not need to be 0. It could be somewhere else. At time 0, maybe you were already 10 miles from home. Maybe. And so the answer would be different. So this is our notation we want to really focus in on. This is the heart of the integrals, the stuff that we're going to do. So this is also known as the definite integral. I can't tell you exactly why they use the word definite and indefinite. Maybe I should be able to, and it's my bad. I don't know if I should be able to or not. But there's 2 terms we need to be aware of. There's the definite integral, and then there's the indefinite integral. The way I remember the definite integral is I get a definite answer. I get a numerical answer out, or I have the ability to get one at least. You know, maybe a and b are just variables. I come up with an equation instead of an actual number, but I created an equation that can do those numbers. An indefinite integral is another word for an antiderivative. It's an antiderivative that represents all possible antiderivatives. So that would be, you know, let's just, an indefinite integral would, and the problem even looks different. Problem looks like this. Notice it doesn't have any intervals. And so you have the integral of some function f of x dx. What is that equal to? Well, it's equal to its antiderivative, plus c, right? So that represents all the possible functions that have lowercase f of x as its derivative.